Assalamu alaikum, students. Can you hear me? Okay. In our last class, we actually started different kind of thermodynamic cycles, and basically we started chapter number 9, and our focus was about studying the heat engines. The heat engines are basically the ones that produces the power output. We discussed that in detail in chapter number 6, and in chapter number 9, we are going to start actually designing and looking at the different kind of designs of the thermodynamic cycles that produces power. And we discussed in an overview about different kind of cycles that we have. Basically, the three cycles that we are going to study in detail are the Otto cycle, the diesel cycle, and the Brayton cycle. From the point of view of PV diagram and the TS diagram, I showed you what kind of cycles do we have, what kind of processes we are going to have within those cycles. Basically, these are the power cycles, but in chapter number 9, the working fluid will be the air. So air is considered the working fluid. So table A17 will be the one which will be more important in this chapter. Later on in chapter number 10, we are going to still study the power cycle, but in that case, we'll have water or steam as the working fluid. So water and steam tables will be important there. Anyways, before moving forward, anybody have anything to ask so far? Anything not clear from the last lecture? So you can ask. Everything is okay to everybody? Anybody have anything to ask? Okay, so let's continue forward. In Otto cycle, basically Otto cycle is the petrol cycle, and obviously we have a piston cylinder device in these kind of cycles. So the petrol cylinder is the Otto cycle. The ideal cycle for the petrol one is the spark ignition cycle. These are also known as the spark ignition cycles. We discussed that before in our last lecture, that these are the kind of cycles which needed in a spark plug for combustion. So let's study different kind of strokes in an Otto cycle. First of all, let me just remind you what is a stroke. When the piston moves from the bottom dead center to the top dead center, or from the top dead center to the bottom dead center, this length is the stroke. So the entire motion from top to bottom or bottom to top is a stroke. So basically, in case of an Otto cycle, we have 4 strokes. The first one is the compression stroke. Then after that, we have the expansion or power stroke, then the exhaust stroke, then the intake stroke. Okay, so let's have a look at these strokes in a bit more detail. So first, initially, we have, let's say we start our condition from the state when the piston is at the bottom level, at the bottom dead center, and the cylinder is filled with an air fuel mixture. So the first thing is that the piston moves up, and the upward motion causes the compression of the air fuel mixture. So that's the compression stroke. Since we are talking about an ideal cycle and all the processes we assume to be ideal, so we say that this compression is an isentropic compression. We discuss about entropy, and so when we say that it is an isentropic compression, that means it is also adiabatic compression. So this entropy, what is the relationship between isentropic and adiabatic? We discussed this in detail in chapter number 7. So, so let's say that we say that this compression is an isentropic compression. So obviously it is also adiabatic compression. And so the compression occurred without any losses and the entropy remains the same. And by the end of the compression, the piston is now at the top dead center. So the first stroke is completed. Then at the second stage, what happened is that now the piston stays on its own location. Now the piston does not move, so the volume of the cylinder remains fixed. But what happened is that ignition occurs, and because of this ignition by the spark plug, we have the combustion that occurs. Okay, so when the combustion occurs, basically what we say is that heat is being added to the air fuel mixture. Okay, so heat is being added to air. Air is considered as our working fluid in these kind of systems. So we say that the heat is added to the air, and now this second step occurred at constant volume. So the volume remains constant. So obviously it would represent by a vertical line. And so heat is being added. Then in the third stage, now what happened is that uh, uh, we have expansion stroke, or you can say that we have because of this power stroke. Obviously, the piston is going to move down, and after the heat has been added, the piston is going to move down, and that is the expansion that takes place at the same time. And then later on, what happens is that we have the exhaust valve that opens, and then so the piston moves back up, and while the piston is moving back up, so the exhaust gases goes out, and once the exhaust gases are gone, then the piston moves back down, and so the air fuel mixture is new air fuel mixture is added into the cylinder. So these are basically the 4 strokes in case of an Otto cycle. If you just consider it, if you just simplify it for our calculation purposes, we represent it like this. So we have an isentropic compression, okay, and then after that we have the combustion occurs, but we say this is a constant volume heat addition. So we have isentropic compression, then we have constant volume heat addition, and then after that we have isentropic expansion. Because of the combustion occur, there will be an expansion. So that's an isentropic expansion. And then after that, we say the constant volume heat rejection. Now this constant volume heat rejection, which is there in the simplified version, we're going to have in reality, we are going to have another stroke here. And that another stroke is the exhaust and the intake stroke. But because when we say that Q going out of the cylinder, what we mean is that all the air fuel mixture, all the exhaust gases going to go out, and the new air fuel mixture is going to come in. So it needs another stroke to take place. So that's why this is the real cycle. In the real cycle, we have the exhaust and the intake needs another cycle to take place. Otherwise, in the idealized one, we just assume that there is Q out, and within this Q out, this another stroke take place. So we'll have so we'll have basically 2 strokes in which the actual cycle occurs, and then we have 2 strokes for the exhaust and intake to occur. So in reality, we have 4 strokes for a complete cycle to take place in reality for these kind of cycles. So the PV diagram is very important here for this. Obviously, in the PV diagram, we're going to always start with the compression. So we'll have initially isentropic compression, then we are going to have constant volume heat addition, then we have an isentropic expansion, and then we have the constant volume heat rejection. So these are the 4 processes of an ideal Otto cycle. Now, explaining these things on paper is obviously because these are the real motion cycles. So explaining things on paper doesn't really helps a lot. So it's more important that you need to actually see what's happening. Now, the only way I can give you I can make you to see is by providing you the videos, and the videos are already provided to you. in the Google Classroom of chapter number 9. So if you can go through with the videos, you're going to see the actual simulation and actual animation for an Ordo cycle operation. So anybody have anything to ask during this explanation? Everything is clear so far?
Yes, sir.
Okay. Okay, now the next thing is that for our point of view, important thing is the calculation. Okay, calculation is very important. So first of all, here basically in chapter number 9, we are applying what we studied from chapter number 1 till chapter number 7. Now, if you remember, now this is if I talk about state number 2 to state number 3, this is basically the constant volume heat addition. Now, if you remember, we already studied in chapter number 4 what will be the amount of Q for a constant volume process. So if you remember, the Q for constant volume process was Q is equals to delta U, okay, or M multiplied by U, or you can say that MCV delta T. So this is basically we studied in chapter number 4. This is the formula from chapter number 4. So we're going to apply it here between state point 2 and 3. The other thing is that here again it's a constant volume, but this is heat rejection. So how much will be the Q? It will be again delta U. Okay. So when we say delta U, obviously U will be greater for 3, U will be less for 2. Okay. So delta U means U3 minus U2 here. And here delta U means U4 minus U1. It's always the higher value minus the smaller value. So this will be for the case of state point 2 to 3 and 4 to 1. Let's talk about state point 1 to 2. It's compression. Okay. Now, if you remember, for the case of compressors, we studied this is compression, and this is expansion. Okay. So if you remember, we studied for the case of compression and expansion in chapter number 5. So we talked about compressors, okay? And the expansion was done in the turbine. Here it is not done in the turbine, but in any case, this is expansion, okay? So if you remember there, we had the formula Q minus W plus, then we have M dot, okay, enthalpy, or I'll say delta H plus delta kinetic energy, okay, plus delta potential energy, and equals to 0. Why? Because we said that these are steady flow, steady state devices, so overall change is 0 with respect to time. Okay, now here in this case, when we talk about compression, first of all, we are saying isentropic compression. And remember, I told you in chapter number 7, whenever we say isentropic, that also means adiabatic. So adiabatic means this term will be 0. The work will always be there since there is compression. Okay, then for this case, since the amount of air going in and the out, both are from the exhaust and the intake valves, and they are of the same dimensions. So there won't be any change in the kinetic energy for the fluid going in and out. So delta kinetic energy will be 0. Delta potential energy will also be 0 because in and out are both at the same locations. So what we are going to have, we are going to have only this thing. W equals to m dot delta H. So here we have, if we want to know what is the amount of work done during this isentropic compression, so work in will be m dot delta H. So here also you're going to put m dot, okay, and here also you're going to put m dot or m, depends, okay. So if you put m dot delta H, so delta H here for this case will be enthalpy of 1 and enthalpy of 2, so it will be H2 minus H1, or here in this case, for the case of expansion, it will be H3 minus H4. Always it will be higher value of enthalpy minus the lower value of enthalpy. So the formulation is very simple for the case of compression or so, or for the case of expansion, and then for the case of heat addition, as well as for the case of heat rejection. And these formulations come from your understanding and your knowledge of chapter number 4 and chapter number 5, which you already covered before. So constant volume processes were in chapter number 4, and isentropic processes are basically in chapter number 5 that we studied. Anyways, we are going to apply it into numericals, and things are going to be more clear to you in that way. So anybody want to ask anything? So far, everything is clear. Okay.
Yes, sir.
Okay, so let's talk about Otto cycle. Okay, Otto cycle, first of all, we already seen that in a regular Otto cycle, we have 4 strokes. Okay, 4 strokes actually make up one complete ideal Otto cycle, one complete cycle of an SI engine. However, we also have another kind of spark ignition engine where we actually have 2 cycles, where we actually have 2 strokes. Okay, the 2-stroke one is a technology which is now not used in reality because there are many disadvantages of this technology. Although within 4 strokes, although you get a power stroke in every 2 strokes, so the power of these cycles are comparatively more. However, there are more losses within these cycles. So again, I would like you to go through the animation videos which I have provided for chapter number 9. They are going to explain you the operation of these Otto cycles, which are actually 2-stroke engines. And also the disadvantages of these 2-stroke engines compared to the 4-stroke ones are there listed. So I want you to go through it yourself, okay? And what are the disadvantages of the 2-stroke compared to the 4-stroke? So there are some of the disadvantages listed here, but I'm not going to go through it with you right now here. I want you to go through it yourself. Okay. Let's talk about the TS diagram for an ideal Otto cycle. So when we draw the TS diagram, so the compression is an isentropic process and the expansion is an isentropic process. So these 2 processes would be shown as vertical lines. And then we have 2 constant volume processes. So first we have the compression 1 to 2, then we have the constant volume heat addition. So Qn is shown here. Then we have the expansion, and that will be isentropic, and then we have the constant volume heat rejection. Okay. So these are the 4 processes. Whenever it is asked to write down the processes of any kind of a cycle, whether it is Otto cycle or any other cycle that you are studying, one important thing is the order. The order is very important. So when it says that isentropic compression, after isentropic compression comes constant volume heat addition. Okay, so if anybody write isentropic compression and after that he writes isentropic expansion, so this will be wrong. So the steps, the sequence is important because we know that after one process, then the next occurs, then the next, and then the next. So all the 4 processes are occurring in a specific sequence, and that sequence is important. Okay, so it's not just about listing down what kind of processes are occurring within the Otto cycle, but also in what sequence. So this is also important. So after isentropic compression comes the constant volume heat addition, then isentropic expansion, then constant volume heat rejection. Yeah, this is possible that somebody, let's say, starts from isentropic expansion, then he will write constant volume heat rejection, then isentropic compression, then constant volume heat addition. So from what point you start the process, that's not important. But what is the sequence? This is important. You need to follow the sequence whenever you are writing the steps. Okay, so suppose if we consider the constant specific heat conditions. So for constant specific heat conditions, okay, now we need to define here one thing, which is one important parameter here, and that parameter is basically the compression ratio. Now, compression ratio we already defined before as well. If you remember, we defined here compression ratio. Compression ratio is basically what? It is the maximum volume over the minimum volume. This is the compression ratio, R. So for an Otto cycle, this compression ratio is very important. Okay, and here if we look here, the compression ratio would be this. This will be the when the piston is at BDC, that's the maximum volume, and when the piston is at TDC, that's the minimum volume. So it's always V1 by V2, or you can say V4 by V2, or you can say V1 by V3 or V4 by V3. So it's higher volume because V1 and V4 are same, and V2 and V3 are same. So it's higher volume, maximum volume divided by the minimum volume. So that's the compression ratio. So suppose if you are considering the constant specific heat conditions, so for constant specific heat conditions, if we just know the compression ratio, which is R, that would be enough to actually determine what will be the efficiency of an Otto cycle. Okay, now there is a specific formulation here mentioned. Okay, you can go through this derivation yourself. This is just with a little mathematical manipulation. We've achieved that the efficiency, thermal efficiency of an Otto cycle will be given by this formula. This formula is 1 minus 1 upon R K minus 1. R is the compression ratio, and K is specific heat ratio. And if you remember, we also studied that there is a specific there is a specific heat ratio, and we studied the value of K or the formula of K in chapter number 4. So K is basically Cp upon Cv, and for the case of air, its value is 1.4. Okay, so this is something that we already know. So if it is a constant, if it is a cold air standard condition or constant specific heat condition, then for that case, this formula can directly predict the efficiency of an Otto cycle. Now you need to remember one thing. This formula you can only apply if it is the cold air standard condition or the constant specific heat condition, or it is said that use the approximate analysis. Okay, if you want to do the exact analysis, for exact analysis, this formula is not valid. When we have the variable specific heat condition, this formula is not valid. You cannot use this formula for the case of exact analysis or the variable specific heat condition. But if it is only the cold air standard condition, or if it is said that use the approximate analysis, or it is said that use the constant specific heat condition assumption, then you can use this formula. Otherwise, for the exact conditions, you cannot use this formula. Okay. This K is sometimes also written as gamma in the book. Okay, so they both are the same thing. Okay, so it's specific heat ratio. So let's have one of the numerical. So we have the air at the beginning of the compression stroke of an air standard Otto cycle is at 95 kilopascal. Okay, so we have air in the beginning of the compression stroke, that will be state point 1. Okay, so compression stroke starts here. So this is the compression stroke starts 1 to 2. So at 1, we have the air at 95 kilopascal and 22 degrees centigrade. So we know that what is the temperature and what is the pressure of the air. So we know what is T1 and we know what is P1. Okay, and the cylinder volume is 5,600 centimeter cube. So that's the total cylinder volume. Okay. So when we say that what's the cylinder volume, that means this is the maximum volume of the cylinder. Okay, the compression ratio is 9. Okay, so we have the compression ratio 9. So R is given. So R is basically 9. So R is V1 by V2 or V4 by V3. This is equals to 9. And 8.6 kilojoules are added during the heat addition process. So that's the QN. Okay. So we know that how much is the amount of heat added during the heat addition process. So that's about 8.6 kilojoule. Okay. So what we need to do is we need to calculate the temperature and pressure after the compression and heat addition process. Okay, so after the compression process, so that means T2 and P2, these are the things that we need to determine. And heat addition process. Heat addition process is from 2 to 3, so we need to know what is T3 and P3. And then what we need to determine what is the thermal efficiency of the cycle. So we need to determine what is the efficiency of the cycle. We need to use the cold air cycle assumptions. So cold air standard assumptions are used. So this is very important when it says that when it says that use the cold air standard assumptions, this explains that what kind of procedure you're going to use to solve the problem. Okay, so that means now you're not going to use table A17. If it is cold air standard assumption, you cannot use table A17. So table A17 is only used for the exact analysis. Okay. So let's start one by one. Okay, first of all, since we know what is the volume of the cylinder, so we know what is V1 and V4. So V1 is equals to V4 is equals to volume of cylinder. Okay, so since we know V1, so we can find out actually what is the mass which is flowing throughout. Okay, so because we know the temperature, we know the pressure, and since it is air, and we can use as an ideal air condition, so we can say that PV equals to MRT. So we know what is P1, we know what is V1, we know what is T1, we know what is R for the case of air, and so we can find out what is the mass of the air flowing through this. So it's the same mass which is then moving from state point 1 to 2, then 2 to 3, 3 to 4, 4 to 1. So mass is not going to change. So it's same. Since the mass is same, and obviously it is air all the time, we consider it to be air all the time. So M and R values does not change. So that means PV by T is constant. PV by T is constant because PV by T is MR, and mass is constant, R is constant. So this whole thing is a constant. When we say that this thing is constant, so always remember one thing, that means we can say that P1 V1 over T1 is equals to P2 V2 over T2, which is same way as P3 equals to P3 V3 over T3, which is equals to P4 V4 over T4. So all these relationships are valid, okay, in this kind of condition. Okay, so first thing, let's start from state point 1 to 2. Okay, when we move from 1 to 2, we know this is an isentropic compression process. Okay, since it is an isentropic compression process, we cannot use table A17 because you have cold air standard condition. So now we have to use the equations which are developed for the isentropic cases in chapter number 7. If you remember, in chapter number 7, we developed 3 equations for isentropic cases, one relating temperatures with the specific volume, or other relating temperature with the pressure, and the third one relating temperature with the volume. Okay, since we need to know what is the temperature and pressure at this point, okay, so we can use the equation for relating temperatures with the volume. Okay, we know what is the volume V1. We can determine what is the volume V2, but at the same time we know what is the compression ratio. So we know that V1 by V2. V1 by V2 is 9. So we know this is 9. Power k minus 1, k value is 1.4, multiplied by T1. T1 is the temperature. T1 already known. So we can determine what is T2. At this point, we determined what is T2. Okay, so this is, we determine it. Okay. The next thing is that we need to determine, we can determine the pressure here. Here the pressure is not actually calculated, but we can determine the pressure from this equation. Okay. So because we know V1, we know V2, and now we know T1, we know T2, we already know P1, we can determine what is P2. So P2 can also be determined. It's actually not done here, but this is, you can do it yourself, determine P2. Okay. The next thing is that now statement 1 to 2 is done, so we have already determined T2 and P2. The next thing is from 2 to 3. 2 to 3 is not isentropic, but 2 to 3 is a constant volume heat addition, and for the case of constant volume heat additions, you have to use the formula Q equals to M delta U, okay? Or for the case of a constant specific volume, we have to use M CV delta T, okay? So it will be M delta U, but delta U can be written as CV delta T. Again, this formulation can only be used from here to here. It can only be used for the cold air standard assumption or the constant specific heat case. So since here we have the cold air standard assumption or the constant specific heat case, so we're going to use this methodology. Okay. Here we already know what is Q. Here we already know what is Q. And we already know what is the mass. CV value, we can get it from CV value. We can get it from the table A2. Okay, it's from table A2 for air. We already know what is T2, so we can determine what is T3. So if you just substitute the values, you're going to get the value of T3. So T3 is determined like this. Okay. The next thing is P3. P3 is not shown here how to calculate, but you can calculate it yourself. Okay. It's very simple. As I told you, M mass is constant throughout the entire cycle, and R is also constant throughout the entire cycle. So MR is constant, so PV by T is constant throughout the cycle. So you can use P2 V2 by T2 equals to P3 V3 by T3. Okay, so now you know T2, you know T3, you know T3, you know T2, you know the volume is same, V2 and V3 is same. Okay, and you know what is P2, so you can determine what is P3. Anybody have anything to ask? Everything is clear so far?
Yes, sir.
Okay. The next thing is that you need to determine what is the thermal efficiency. Determining thermal efficiency, because it is the cold air standard assumption, we can directly use the formula for the case of Otto cycle. When we know the compression ratio, we can determine what is the thermal efficiency. Remember, you can use this formula only when you have the cold air standard assumption, or it is said that use the approximate analysis, or it is said in the problem that use the constant specific heat values. But for exact analysis, this approach cannot be used. So this is okay here because we are using the cold air standard assumption. So we have determined the thermal efficiency and all the things which were needed to be determined for this example. So this example is finished. If anybody have to ask anything, any step is not clear, please ask. Everything is clear? Are you catching up with me? Okay, so let's have another problem here. An ideal Otto cycle has a compression ratio of 8. So again, it is an Otto cycle, and the compression ratio is 8. So R is given. At the beginning of the compression process, air is at 100 kilopascal. So this is the point. Okay, so at the beginning of the compression process, obviously, whenever we have to use the Otto cycle, so PV diagram would be very simple: two vertical lines, and then they just connect them together. So that's 1, 2, 3, 4. Okay. So at the beginning of the compression process, air is at 100 kilopascal and 17 degrees centigrade. Okay, so we know what is T1 and P1. So this will be T1, and sorry, this will be P1, and this will be T1. And 800 kilojoule per kg of heat is transferred to air during the constant volume heat addition process. So this is Q in. Okay. Accounting for variation of a specific heat of air with temperature. This is very important. When it says that accounting for the variation of a specific heat of air with temperature, so that means you need to use exact analysis. That means you need to use table A17 here. Okay. So a table A17 will be used here. Determine the maximum temperature and pressure that occur during the cycle. So obviously the maximum temperature and pressure is going to occur at state point 3. So we need to determine T3 and P3. This is something that we need to determine. The net work output. Okay, so workout network. And thermal efficiency and the mean effective pressure for the cycle. So thermal efficiency we need to determine, and the mean effective pressure we need to determine. Also determine the power output from the cycle in kilowatt for an engine speed of 4,000 RPM. Assume that this cycle is operated on an engine that has 4 cylinders with a total displacement volume of about 1.6 liter. We're going to look at it in the end. So let's start solving the problem. So we have a situation like this. This is our PV diagram. So statement 1, 2, 3, and 4. This is the Q in process. Here from 4 to 1, we have Q out. We have 2 isentropic processes. Okay, we know what is we don't know the specific volume for any state, but we know one thing, that the compression ratio is 8. That's mentioned, that the compression ratio is 8. Okay, so let's just start with the solution. First of all, 1 to 2 is an isentropic process. Since it is an isentropic process, so you're going to use table A17. So A17 is for isentropic processes. Now here we have the volume ratio. The compression ratio is basically the ratio between the volumes. So we know what is V1 by V2. Okay, so this is known. This is actually 8. So when we know the volume ratio, so we are going to use the VR value. VR value to determine T2. Okay, we already know what is T1 and P1. So at state point 1, we know what is T1 and we know what is P1. It was mentioned as 100 kilopascal and 17 degrees centigrade. Okay, so our logic will be we are going to go into table A17. Corresponding to T1, we are going to determine what is VR1. Then using VR1 and V1 by V2, we're going to determine what is VR2. And then once we determine VR2, we're going to go back into the table. We're going to find where is VR2, and then corresponding to VR2, we're going to determine what is T2. Okay, so let's have a look at it. So T1 is 290 Kelvin. Okay, so we can go into the table here. Okay, table A17 for 290 Kelvin. So this is 290. Corresponding to 290, we can determine what is VR. So VR will be 676.1. Okay, so we go back here. So this is, okay, also we will determine U1 at that point, because here at T1 we can also determine U1 value. So that will be the U value, U1, 206.91. Okay. So we're going to get this and this, okay, corresponding to VR1, then we are going to use this relationship, VR2 by VR1 equals to V2 by V1, and we're going to get what is VR2. So VR2 comes out to be 84.51. Okay, so now we're going to look in the table. Where is 84.51? So 84. So if you look at the VR values, 84.51 would be in between the two, so you need to interpolate. So once you interpolate in between the two, so you can determine what is the U2 value also by interpolation, and you can also determine what is the temperature value by interpolation. Okay. So it will be between 650 and 660. So the value comes out to be 652.4 by interpolation. Also U2 value comes out by interpolation. Now, once you have U2 and T2, then you can use this relationship P2V2 by T2 equals to P1V1 by T1. Okay. Now here we already know what is the compression ratio. We know temperatures. We know the initial pressure, so we can determine what is the pressure P2. So here we determined P2 and T2. The next thing is that heat addition. Heat addition Qin is equals to U3 minus U2. So Qin is already given. U2 you already know. Okay, we already determined U2 now here in the last step. So we're going to use these two things to determine U3. Okay, and then once you have U3, corresponding to U3, you can determine what is T3 and VR3. Okay, so U3 is 1275.11. If we go into the table, 1275.11 is basically U value. 1275.11 would be in between these two. So corresponding to that, you can determine what is VR3. So you need another interpolation and another interpolation to get the temperature T3. So T3 comes out to be 1575.1, VR3 is 6.108. Then once we have determined this thing, then we can use P3V3 by T3 equals to P2V2 by T2 to determine what is P3. So now you have determined T3 as well as you have determined V3. In the same way, we are going to repeat step 4, because we know what is the compression ratio of V4 by V3. So we already know what is VR3. We will determine what is VR4, and then corresponding to VR4, we are going to determine what is T4 and U4. Okay, so now you know U's at all point, you know temperatures and pressures at all point. So now we can determine that what is the amount of heat out. So heat out will be U4 minus U1. So U4 minus U1 comes out to be this much. Okay, and once you have Q in and Q out known, then you can determine W net, because W net is Q in minus Q out. This is something you studied in chapter number 6 for the case of heat engines. If the heat engines, for the heat engines, the work output is Q in minus Q out. So it comes out to be 418.17 kilojoule per kg. Thermal efficiency is work net over Qn. Again, we determined this thing from chapter number 6. So we already know now what is work net, and we know that what is Qn. So we just substitute the values, we're going to get what is the thermal efficiency. Suppose if it is said in the question that use the cold air standard assumption, then you could have used directly this formula. And if suppose you use directly this formula, then in that case, if you substitute the value of the compression ratio, you can determine that the thermal efficiency is about 56.5%. So, but anyways, you're not going to use this methodology. This is the methodology that we are using because we are solving the problem for the case of variation of specific heat with temperature. Okay, the next thing is determine the mean effective pressure. So mean effective pressure is work net divided by V1 minus V2. Okay, so we already know what is V1. We can determine V1 by because we know what is T1, and we know what is P1, and we know what is R for the case of air. So we can just substitute the values, and we can determine that what is V1, and then we can just substitute the V1 here into the main formula for mean effective pressure. We can calculate what is the mean effective pressure. The last part is if it is said that we have 4 cylinders, okay, and we know what is the volume of a single cylinder. Okay, we know what is the specific volume for the air in this case, so we can determine that how much is the mass of the air moving through all these processes. So if you just multiply the work net by the mass, so we can determine actually that what is the amount of energy generated in each cycle. Now here it is written that let's say that the engine is moving at 4,000 revolution per minute. Okay, so per minute, if we just multiply by the number of kilojoule that is generated per cycle, so we are going to actually determine that how many number of kilojoules are generated per minute. But we have to understand one thing, that this is an Otto cycle, and after every 2 revolution, 1 cycle is completed. Okay, so we have to divide by 2, and this is per minute. So if we divide by 60, we're going to get the values in kilowatt. So that will be 26.8 kilowatt. And with this, our solution of this problem is finished. So if there is anything within the solution which is not clear to anybody, any step, please ask. Is the solution clear?
Yes, sir.
Okay. So anyways, this was about the Otto cycle. With this, we finished our Otto cycle, and now next step, we're going to move towards the diesel cycle. So if anybody have any question, you can ask. Otherwise, let's have a break of 10 minutes, and then after that, inshallah, we're going to start our diesel cycle. Please put your attendance in the chat box so that I will mark your attendance. Okay, so now since we have already covered the Otto cycle, the next is the diesel cycle. As I explained this before in the last class, that the only difference between the Otto and the diesel cycle in terms of their diagram is that when you draw the PV diagram, so when you draw the PV diagram, so in this case, for the case of a diesel cycle, you're going to have, instead of having two vertical lines, you're going to have one horizontal and one vertical line. Okay. So this is how we're going to have our diesel cycle. So here we have the isentropic compression, then we have the constant volume heat addition, the constant pressure heat addition, then we'll have isentropic expansion, and then we'll have the constant volume heat rejection. So here, instead of having constant volume heat addition, as in case of the Otto cycle, now in case of the diesel cycle, we're going to have the constant pressure heat addition. That's the only difference. So in terms of the PV diagram would look like this. So you're going to have a horizontal line and a vertical line. Okay, so that's a constant volume process, and this is a constant pressure process. And then obviously the compression and the expansion, they both remain isentropic. Now here there is one more thing. Since we already studied in case of the Otto cycle, we studied one ratio, which is the compression ratio. And compression ratio was basically what? It was the maximum volume by the minimum volume. So here we are still going to have the compression ratio as the maximum volume divided by the minimum volume. The maximum volume here is V1 or V4. It's either V1 or you can write V4. This is the maximum volume, and the minimum volume, it's not V3 anymore. So minimum volume is only V2. So we have V1 by V2 or V4 by V2. This is the compression ratio. However, now since we have another volume V3, okay, so we're going to have another ratio, and we say it's cutoff ratio. And cutoff ratio is basically what? It is V3 by V2. Okay, so V3 by V2 is the cutoff ratio. Now, let me tell you the idea of the cutoff ratio is that in case of the Otto cycle, what happened was that when the piston moves after compression, the piston actually stops at the position, and then we had the spark plug which does the combustion, and this combustion takes place at constant volume. This was what happened in case of the gasoline cycle or petrol cycle or Otto cycle. Okay, so this is what happened there. Here in this case, in case of the diesel cycle, what we do is that we don't have the air-fuel mixture. We just have the air, and the air is compressed to whatever the compression ratio is. And when the piston is at the top position, okay, then the fuel is injected. So we don't have a spark plug. The fuel is injected. The air is already heated to such an extent that as soon as the fuel is injected, the fuel burns. So the combustion occurs at the same time. But while the combustion is occurring, the piston starts moving down as well. So the pressure remains constant. Now the fuel is being injected till whatever the amount of fuel is required to be injected has already been injected. Okay, so while the fuel is being injected, the volume keeps on increasing. Okay, and so the point when the fuel injection is cut off, when the fuel injection stops, that point is the cutoff point, and that's why the cutoff ratio is V3 by V2. So V2 means the point when the fuel injection starts. V3 is the point when the fuel injection is cut off, when the fuel injection stops. Okay, so that's why V3 by V2 is the cutoff ratio. And then after that, the process occurs in the same way as before. On the TS diagram, practically there won't be much difference. So we're going to have two isentropic processes, so two vertical lines. And then we are going to have one constant pressure process, which is the heat addition. And then we'll have the constant volume process, which is the heat rejection. The only difference is that the constant pressure process is a little more inclined compared to the constant volume process. Okay, so this constant pressure process is more closer to horizontal. It's not horizontal, but it's more closer to horizontal. Okay, and the constant volume is a bit more inclined. So this is how the diesel cycle looks like. Anyways, the processes within the diesel cycle are all the same. Only the difference is instead of the spark plug, we have the fuel injector, and there is a start point of the fuel injection, and there is an end point of fuel injection. And during the fuel injection, the piston keeps on moving. So that's the only difference between the diesel cycle and the Otto cycle. And the thing is that the kind of fuel which is used for the diesel cycle is diesel. We cannot use gasoline or petrol for the case of diesel cycle because the gasoline and petrol cannot hold up till that pressure, which is actually which could be achieved by the diesel cycle. So we have different fuels for these kind of cycle. So anyways, if you want to look at the animation of these kind of processes, so the animation videos are already provided to you in the Google Classroom against this chapter. So you can watch those videos, and it's going to really help you understand the animation processes. Okay, thermal efficiency of the diesel cycle. Previously, we determined that for the case of Otto cycle, if it is the cold air standard assumption, then the efficiency of the Otto cycle depends or is a function of R, which is the compression ratio. For the case of diesel cycle, it's a function of R and also RC, compression ratio and cutoff ratio. Okay, both. Now, what is the relationship? How it's a function? There is a small mathematical derivation, and that derivation is there in the book as well, and it's provided in the slides. So go through it yourself, self-study. Okay. Well, I will just discuss the end result. The end result is we have the thermal efficiency of the diesel is 1 minus 1 over RK minus 1 into RCK minus 1 divided by K into RC minus 1. So it's all about K, R, and RC. So we can actually directly determine. Again, this formula is only utilizable if you have the cold air standard assumption, or if you have the approximate analysis, or if you have the constant specific heat assumption valid. Okay, suppose if it is said in the question, use the variable specific heat or use the exact methodology. So for exact methodology, you cannot use this formula. Okay, so for exact methodology, there is only one formula which you studied in chapter number 6, that the work output divided by Q in is going to give us the efficiency of the heat engine. Typically, the efficiency of a diesel engine varies with the compression ratio. Okay, so if the compression ratio increases, obviously the efficiency increases. Okay, at the same time, the cutoff ratio also affects the efficiency of the diesel engine, and their variation is shown here. So you can go through the graph yourself. We're going to start with the numerical of the diesel cycle. If anybody want to ask any question, you can ask. Everything is clear so far? Is there any concept which is not clear? Please ask. Anything which is not clear?
Clear, sir.
Okay. Okay, so let's see this example. So we have an ideal diesel cycle. First of all, it's a diesel cycle. So we can just see it from the name. So we have an ideal diesel cycle. Air is the working fluid within this cycle, and it has a compression ratio of 18, so that's R, and a cutoff ratio of 2, so that's RC. Okay, At the beginning of the compression process, the working fluid is at 100 kilopascal, 27 degrees centigrade, and 1917 centimeter cube. So we know the initial temperature, pressure, and the volume. So if you draw the PV diagram for this, there's going to be a horizontal and a vertical line. So that's 1, 2, 3, 4. So at state point 1, we know all the 3 parameters. Utilizing the cold air standard assumption. So here we cannot use table A17. Table A17 cannot be used because it's cold air standard assumption. We need to determine the temperature and pressure of air at the end of each process. So we know for state point 1, but we need to know at 2, 3, and 4. Then we need to know that what is the net work output and the thermal efficiency of this diesel cycle and the mean effective pressure. So since we are going to be using the formulas which we developed for different isentropic processes, so once again, we need to use the values of Cp, Cv, and K from the table A2. So the Cp value for air, see this is the Cv value for air, K is 1.4, R is 0.287 kilojoule per kg Kelvin. These are the values we are going to use. Here one more thing is that since it's the same mass which is actually going through all the processes, so the mass is constant and R is constant, that means PV by T is constant, so that relationship is valid. So in any case, P1 V1 by T1 equals to P2 V2 by T2 equals to P3 V3 by T3 equals to P4 V4 by T4. So this thing is valid in any case. So let's start looking at the solution of this problem. So we have since we know what is the volume V1, okay, and we know what is the compression ratio, we can determine what is V2. We also know what is the cutoff ratio, so we can determine V3, because cutoff ratio is V3 by V2. The compression ratio is V4 or V1 by V2. Okay, so V4 and V1 are same. So we know that what is V1, we know what is V4, V2, and V3. So we determined all the volumes. Straight away, now we can move towards process 1 to 2. Process 1 to 2 is isentropic. So it's isentropic compression. So we cannot use table A17 because it is cold air standard assumption. So we are going to use the formulas developed for the isentropic processes. So for the case of temperature, since we know the volume ratio, so we can determine what is T2 and we can determine what is P2. And so here we determine what is T2 and P2 from this methodology, between using the equation for the relationship between temperature and volume, and using the equation for the relationship between pressure and volume. So we know now all the properties at state point 2. For state point 3, again, we know that state point 3 is a constant pressure process from 2 to 3. So whatever the pressure at 2 will be the same as pressure at 3. So we know what is pressure at 3. Then we also know that this equation is valid throughout the cycle. P2 V2 over T2 equals to P3 V3 over T3. So we can use this to actually determine what is T3. So now what is P3 and T3, we have already determined that. Then in the same way from 3 to 4, again, we are going to use the isentropic relationships, because 3 to 4 is an isentropic expansion. So for an isentropic expansion, we have the isentropic relationships between temperature and pressure and the volume. So we're going to use these to determine what is T4 and P4. So now we know all the temperature, pressures, and the volumes at all the state points within the diesel cycle. The next thing is that we need to determine what is the work output of the diesel cycle. Okay, so for that, first we need to know the mass. Mass you can determine from any state point, because now you know PTV values for all the state points. Here it is determined from state point 1. So we can use P1 V1 over RT1 to get what is the mass of the air. So the mass of the air comes out to be 0.00223 kg. Now, once you have this thing, you can determine what is the amount of heat added, Q in. So Q in is basically M H2 minus H3. Remember, this is now constant pressure process. And we determined from chapter number 4 that Q is equals to delta H if it is a constant pressure process. This is from chapter 4. We determined it. So here, this is a constant pressure process. So Q is equals to M delta H, or we can write it as MCP delta T because it is the cold air standard assumption or the constant specific heat values we are going to be using. So we know what is CP, we know what is T3 and T2 M, so we can determine what is the amount of heat in. The next thing is we can determine how much is the heat out, but for this we are going to use, because it is a constant volume process, so Q is equals to delta U. So it will be MU4 minus U1 or MCVT4 minus T1. Just substitute the values, so you're going to get what is Q out. Work net will be Q in minus Q out. Okay, this is from chapter 6. Okay, and the thermal efficiency is again also from chapter 6. That it is work net over Q in. So that's the thermal efficiency. So this will be the thermal efficiency of this diesel cycle is about 63.2%. The mean effective pressure is the work net over Vmax minus Vmin. We already know what are those volumes, V1 and V2, and we know what is work net, so we can actually determine what is the mean effective pressure. So that's the end of this problem. The problem is lengthy, but it is not complicated because the steps are almost similar throughout. If there is anything within the solution of this problem which is not clear to anybody, please ask. Everything is clear.
Yes, sir.
Everything is clear?
Yes.
Okay. Okay, now let's talk about next. We have two another kind of cycles which we are just going to discuss in a brief. We are not going to solve any numerical related to that, and these are the Stirling and the Ericsson cycles. Both in the case of the Stirling and Ericsson cycles, what happened is that we instead of having isentropic processes, we replace them with isothermal processes. Okay, so this is the main difference. So for the case of the Stirling cycle, okay, we have two constant volume processes. Okay, and instead of having two isentropic processes, we have two isothermal processes. So the temperature is constant. Okay, so we have constant temperature heat addition, then the constant volume regeneration, constant temperature heat rejection, and constant volume regeneration. One of the main thing about these cycles is that they have the combustion process or the heat addition process occurring not in the cycle, but it's occurring actually outside the cycle. So you have some we have some videos of the Stirling and the Ericsson cycle there within the Google Classroom. I have uploaded them, so you just watch those videos, and it's going to explain you all the steps of these cycles. But anyways, we are going to study a Stirling and Ericsson cycle just a little bit, and we're not going to go into much details of it. The next thing is the Ericsson cycle. In the Ericsson cycle, it's very similar to Stirling cycle, but the only difference is that all the constant volume processes has been replaced by the constant pressure processes. So whenever you have a constant volume process, you're going to have a piston cylinder assembly. But when you don't have constant volume process, then you don't have piston cylinder assembly. So here we have replaced the piston cylinder assembly with an actual compressor and an actual turbine. Okay, and so we have the constant pressure processes here. Again, we don't have isentropic compression and isentropic expansion. We have, in fact, isothermal heat addition and isothermal heat rejection processes. So this makes up the Ericsson cycle, which is composed of constant temperature heat addition, then constant pressure regeneration, constant temperature heat rejection, and constant pressure regeneration. Again, you have a few videos related to the Ericsson cycle, their operation, mentioned in the Google Classroom. So I want you to go through them. And what are the basic parameters of a Stirling and Ericsson cycle? These are mentioned here. You can go through them. Next is the Brayton cycle. Brayton cycle is actually the more important one, where we are going to study it in more detail and study its modifications as well, and do the numerical problems associated with the Brayton cycle. This we are going to do after 5 minutes. Let's have a break of 5 minutes, and after that we are going to start with the Brayton cycle. If anybody have any question, you can ask.
No question, sir.
Okay, so let's have a break of 5 minutes, and then we are going to start with our Brayton cycle. Okay, so the next is the Brayton cycle. Since we already studied the Otto cycle and the diesel cycle. Now, in case of the Brayton cycle, as I have mentioned you, that now we don't have in the PV diagram, specifically in the PV diagram, we don't have any vertical line at all. Okay, so in the PV diagram, we're going to have two horizontal lines because both are the constant pressure processes. So this will be our Brayton cycle. So state point 1, 2, 3, 4 in the same way. So since now we don't have any constant volume process, so now we don't need to have any piston cylinder inside. So whenever we don't have constant volume process, we don't have piston cylinder. Here, what we are going to have, we are going to have a compressor and the turbine for the compression and expansion process. So compressor is there for compression. Between the state point 1 to 2, we have the compression from 1 to 2. And then from 2 to 3, we have the constant pressure heat addition. So it's basically the combustion chamber. The combustion chamber, within the combustion chamber, heat is added. How is heat added? Because you put the fuel and you do the combustion, so the heat is automatically added. However, this is a process because this combustion chamber, it's open for from the inlet and the exhaust. It's inlet and exhaust are open all the time, so the combustion is occurring and the inlet and exhaust are going on and on. So it's going to be a constant pressure process from 2 to 3. Then after that, it enters into the turbine exhaust gases of the combustion chamber, and then the expansion occurs. Okay, so basically the pressure reduces from 3 to 4. Okay, and then after that we have 4 to 1 is a constant pressure heat rejection. So it's basically the exhaust that occurs in the real cycles. But here in the ideal cycle, what we do is that we connect them together, showing it in the form of a cycle. So that becomes a closed cycle. But in reality, it's going to be an open cycle. So the exhaust gases go out, and then the fresh air is now taken out, is taken in to the compressor again, and the cycle continues. Both the compressor and the turbine, in case of the Brayton cycle is also known as gas turbine cycle. Okay, so both the compressor and the turbine are connected with a single shaft. We know that the compressor needs work input. Okay, here we are not supplying the work input as electrical energy. We are not supplying electricity. What we are doing is that we are directly supplying the mechanical energy by connecting the compressor with the turbine. Now the turbine is going to give us the workout. Okay, and this workout is a mechanical work output. But what we do is that part of the work output is then used by the compressor as work in. Okay, and so what we get out of the turbine is basically the net work output. And what is the net work output? It's the total workout minus the work in taken by the compressor. So that will be the work net. So this is something that we get out of this Brayton cycle. Normally what happens is that we connect this turbine to the electric generator, okay, and then the electric generator produces electricity. Okay, so this is something that happens in reality. Okay. So this is our Brayton cycle. So the processes within the Brayton cycle will be the isentropic compression, then we have the constant pressure heat addition, then we have an isentropic expansion, then we have the constant pressure heat rejections. These are the four processes that takes place inside the Brayton cycle. This is the schematic diagram. This is the idealized cycle because we have replaced the combustion and the heat rejection in the form of a heat exchanger, just taking up the heat in and throwing the heat out. So this is the PV diagram. and these are this is the TS diagram. TS diagram would again look like the same in the case of the Brayton cycle. So we have two isentropic processes, 1 to 2, which is the compressor, 3 to 4, which is the turbine. Okay, and then we have two constant pressure processes. So we have the constant pressure heat addition within the combustion chamber from 2 to 3, and then we have the constant pressure heat rejection, which is the exhaust going out and the new air taking in from the outside. So these are the TS diagram and the PV diagram. Again, we have, if suppose if we have the constant specific heat values, or if we are doing the approximate analysis, or the cold air standard assumptions are valid, then in that case, now here we are going to have another thing, because now we don't have constant volumes. Okay, so here, but we know one thing, that we have two constant pressures. So this is the high pressure, PH, we can say, and this is the low pressure, PL. So the ratio of the pressures, PH to PL, is now known as pressure ratio. So this is the high pressure to low pressure. Or you can say this is P2 or P3, because 3 and 2 are the same, divided by P1 or P4, because P4 and P1 are same. These are the low pressures. Okay. So previously, if you remember, we had the compression ratio. We discussed about the cutoff ratio in the diesel cycle. And now we have another thing, which is the pressure ratio, which is RP. So here, suppose if we have RP and we have the constant specific heat assumption valid, then for that case, the efficiency of the Brayton cycle can be determined directly from this formula. This formula is developed by doing a little mathematical manipulation within these equations as shown here. So you can just go through it yourself. The thermal efficiency of the Brayton cycle is 1 minus 1 over Rp power K minus 1 divided by K, where Rp is the pressure ratio. Now, for the case of the Brayton cycle, what we realize is that we can increase the efficiency of the cycle by increasing the increasing the temperature in the combustion. Okay, so this is our combustion chamber. This is our combustion chamber, and we are doing combustion here. So the more combustion we are going to do, T3 is going to rise. Okay, so the more T3 is going to rise, automatically the efficiency of the Brayton cycle is going to rise. But there is a limit, because the turbine is made up of steel. Okay, so what happens is that when the T3 rises too much, then there is a possibility that it could actually melt the turbine or actually deform the turbine. So we can run the turbine only under the condition that we have a limited T3, that we cannot exceed the T3 with a certain limit. So if that limit is reached, then if the T3 is exceeded beyond the limit, then it's going to damage the turbine. So the efficiency of the Brayton cycle is actually limited by the temperature going out of the combustion chamber. Okay, so by the maximum temperature within this Brayton cycle. So we have a limited maximum temperature, and that limit of maximum temperature is actually going to limit the efficiency of the Brayton cycle. So we have this thing shown here. So that maximum temperature which could be reached is going to limit, and eventually is going to limit everything. So this is also going to limit the pressure ratio, that what pressure ratio that we can actually achieve. Now the Brayton cycle has two major applications. The first, one of the application is in the aircraft industry. So it is used for the aircraft propulsion. Okay, so basically when you have the airplane engines, they are basically operating on Brayton cycle. Okay, with a little modification. That's why we've given it a new name as a jet propulsion engine. We're going to study after the Brayton cycle. But anyways, it is used in the aircraft industry and also for the electric power generation. Okay, so we can just directly connect this Brayton cycle with the generator. The turbine of the Brayton cycle, when connected with the generator, produce electricity. So these are the two major utilization. We have another terminology here within the Brayton cycle. We call it the back work ratio. Okay, that's basically, it's a fraction of the turbine work used to drive the compressor. Okay, because we know that whatever the output of the turbine, part of it is used to run the compressor, and then the remaining is basically your work net. Okay, so what is the fraction which is being used by the compressor is known as the back work ratio. So let's have a problem here. The pressure ratio of an air standard Brayton cycle is 4.5. That's the pressure ratio, RP, and the inlet conditions to the compressor are the temperature and pressure are given. The turbine is limited to a temperature of 827 degrees centigrade, so that's T3, that's limited. Okay, and the mass flow is 5 kg per second, so that will be m dot. Determine the thermal efficiency, the net power output, and the back work ratio. Assume constant specific heats. Since we can assume the constant specific heat, so we can directly get the thermal efficiency using the pressure ratio. So that's the formula here. So that's the formula of efficiency using the pressure ratio. Just substitute the value of the pressure ratio and you can get what is the thermal efficiency of this Brayton cycle. So it's about 34.9%. And the next thing is that we need to determine the net power output. Okay, so the net power output actually depends upon how much is the work input for the case of the compressor, as well as for the case and the work output of the turbine. Okay, so 1 to 2 is our compressor. So here you can see. So 1 to 2 is the compressor, and 3 to 4 is the turbine. And so basically what we have is that for the case of the compressor, W is equals to m dot H2 minus H1. For the case of turbine, these are by chapter number 5. In chapter number 5, we studied the turbine and the compressor, so we can determine what is the work output. For the isentropic case, obviously it will be considered as adiabatic, so Q will be 0. We don't have any changes in the kinetic and the potential energies, so definitely the only thing left is the change in the enthalpies. So the work in for the case of compressor will be again the change in enthalpy, and the work out for the case of the turbine will again be the change in the enthalpy. So work out for the compressor, work in for the compressor will be m dot H2 minus H1. Work out for the turbine will be m dot H3 minus H4, and their difference is going to give us the net work output. Okay, so this is what's done here. So m dot into work of the turbine minus work of compressor. Work of the turbine is H3 minus H4. Work of compressor is H2 minus H1. And we can just replace it by Cp, T3 minus T4 minus T2 minus T1. Cp, why we replace H by Cp? Because these are the constant specific heat we are applying. If it was not constant specific heat, then you had to use table A17. We could not apply this formula. Anyways, for the isentropic relationships, these are the isentropic relationships that we can use between the temperatures and pressures. So we can determine that what is the temperature T2 and T4. Then we can just substitute the values of temperatures. In the formula, we can get what is the work net. The back work ratio could be determined as the work of the compressor divided by work of the turbine. Work of compressor is H2 minus H1. Total work of the turbine is H3 minus H4. So m dot is same, so that it's going to be cancelled. M dot Cp, both are going to be cancelled from the numerator to the denominator. So when we apply the constant specific heat, it's just the ratio of the temperature differences. It will be T2 minus T1 divided by T3 minus T4. So just substitute the values, you're going to get the back work ratio, and that's it. So this is about the Brayton cycle that we have started. We are going to continue forward with this, inshallah, in our next class. But for this class, we are going to end at this point here. So if anybody have anything to ask, you can ask. Do you understand the problem solution here, this one? Is there anything which is not clear within this problem solution?
So can you show me the solution for C part?
See about the backwork ratio?
G.
Yes, yes. The backwork ratio is here. Backwork ratio is basically what? It is the work of the compressor divided by the work of the turbine. Okay. Now work of the compressor is basically what? It will be m dot h2 minus h1. It will be m dot h2
So
minus
it's
h1.
basically a ratio, sir?
It's a ratio. And work of the turbine will be m dot h3 minus h4. Okay. Now here, since it is constant specific heat, we can write m dot cp T2 minus T1. Here we can write m dot Cp T3 minus T4. But here m dot will cancel, Cp will cancel. We're going to just have the ratio of the temperatures with us.
Okay, sir.
Okay. Anything else within the solution which is not clear to anybody?
Yes, sir.
Okay. So with this, we are going to stop our lecture today here. The Brayton cycle is a big one. We're going to study a lot in it, but we're going to continue it in the next class, inshallah, next week. So anybody have anything to ask, you can ask. Otherwise, the class is over. You can leave the class if you want.
Okay, sir. Khuda Hafiz.
Okay.